For nearly a century, the Middle East, and specifically Saudi Arabia, has served as the undisputed epicenter of global fossil fuel production. Despite sitting on top of some of the largest proven oil and gas reserves on Earth, the region is now aggressively pivoting to solar power. This strategy follows the logic of international markets and local geography. It is a calculated move toward fiscal and resource preservation. The transition is a response to engineering and economic realities. The move to solar is a requirement for maintaining regional energy dominance in the 21st century. To understand the infrastructure of the future, engineers have to look past the oil fields and examine the unyielding laws of energy economics. Building a permanent national infrastructure on a volatile, finite resource carries a severe macroeconomic risk, regardless of how abundant that resource currently appears. This is the water well principle. A village pulls from a finite well. As demand surges, the water level drops. Discovering new wells might temporarily crash prices, but depletion continues. The solution: shift to a self-replenishing source, selling the remaining finite reserves globally. The pivot to solar is driven by long-term financial survival and macroeconomic stability, creating the structural logic for a renewable-first grid. The law of conservation of energy dictates that we cannot create power, we can only convert it from one state to another. Most traditional electrical grids rely on taking chemical or nuclear energy and converting it into thermal energy. The mechanical baseline is clear. Fuel enters a boiler, creating intense steam pressure that spins a turbine to generate electricity. Scaling this combustion loop to maintain a 37-gigawatt baseload means the Saudi grid burns millions of barrels of oil and gas daily. Atomic fission provides an alternative, replacing chemical fire with a nuclear reaction to generate the same steam cycle. However, maintaining a nuclear baseload requires executing against extreme safety, environmental, and infrastructural tolerances. When those tolerances fail, the results dictate global policy for decades. The destruction of the Chernobyl reactor exposed hundreds of thousands to radiation. Following Fukushima, nations with deep engineering histories, such as Germany, began phasing out their entire nuclear infrastructure. Traditional power generation, whether fossil or nuclear, physically tethers a national grid to either volatile fuel supply chains or massive mechanical and radioactive risks. Burning fossil fuels at a utility scale produces millions of metric tons of carbon dioxide and toxic sulfur oxides, directly degrading atmospheric chemistry. These gases create the greenhouse effect. Solar radiation enters the atmosphere freely, but the resulting infrared heat is trapped by the chemical barrier, unable to radiate back into space. The global intervention to this pollution began in 1997. The Kyoto Protocol established the first legal mandates for industrialized nations to reduce their emissions. Those initial mandates evolved into the 2015 Paris Agreement, cementing strict climate frameworks across international borders. This dashboard illustrates the carbon market's financial enforcement. If a plant surpasses its limit, it triggers an immediate penalty. Facilities must pay steep fines, completely overhaul generation technology, or purchase expensive carbon credits, transforming emissions into a measurable liability on a corporate balance sheet. Clean energy has moved to the center of the balance sheet. Financial penalties applied to traditional plants by global carbon markets make clean generation the only viable path forward. If traditional combustion is financially penalized, which renewable alternative works for a desert grid? Wind generation requires a rigid operational baseline, continuous sustained wind speeds of at least 5 meters per second. The infrastructure also carries significant drawbacks. Turbines interfere with telecommunications, generate noise pollution, and require expensive infrastructure to reach high-altitude currents. Hydroelectric power eliminates those issues, but it introduces a heavier physical requirement: massive, continuous volumes of water displacement. For most desert topographies, hydroelectricity is geologically impossible. While facilities like the Wadi Bish Dam exist, they are highly localized and cannot support a national baseload. Biomass generation, burning agricultural waste and forests, is equally constrained. It merely recycles carbon back into the atmosphere and demands heavy logistical chains. By strict process of elimination, wind, hydro, and biomass fail as primary baseline solutions for the region. The geographical and meteorological constraints are too high. This leaves solar photovoltaic power as the most effective choice for the Middle Eastern geographic reality. This comparison isolates the engineering advantage. On the left is the mechanical complexity of traditional generation, boilers and high-pressure turbines. On the right is a static, solid-state solar panel. This design represents a departure from traditional methods. By converting photons directly into an electrical current, the system removes the mechanical turbine entirely. This solid-state system yields clear operational benefits. It produces zero noise, zero emissions, and allows for rapid modular installation. There are engineering trade-offs. PV systems generally have lower conversion efficiencies, suffer performance drops when shaded, and require large-scale battery banks to supply power through the night. Yet, despite the storage challenges, solid-state power generation disrupts over a century of turbine-based electrical engineering. The extreme geographical assets of the Arabian Peninsula neutralize these engineering drawbacks. First, the region possesses vast, non-arable land masses. Building utility-scale solar arrays requires massive acreage, and the desert provides this without displacing agriculture. Second, the landscape features a total absence of natural shading. There are no forests to block the horizon, and persistent cloud cover is extremely rare, ensuring a stable generation curve. Looking at this heat map, the ultimate advantage is clear. The region sits at the peak of global irradiance metrics, yielding up to 12 hours of usable sunlight every day. This exceptionally high daily yield mathematically compensates for the lower baseline conversion efficiency of the panels themselves. Mastering solar energy has become the baseline requirement for future grid infrastructure. It is the primary engineering path toward 21st century energy security.